Welcome to this explainer. Whether you're just scrolling through your TikTok feed, checking a dash cam recording of a fender bender, or arguing over a super controversial sports replay, video is literally everywhere. And today, we're decoding one of the absolutely most fascinating frontiers in artificial intelligence right now, how machines actually process and understand all that video. We're going to explore video language models, and we're diving deep into the world of temporal tokens and the sort of hidden magic of temporal grounding. So if you've ever wondered how an AI goes from just staring at static, lifeless pixels to truly comprehending time and motion, well, you are in the exact right place.
To start things off, we really have to ask a foundational question. Is a video basically just a big stack of photos? And the short answer is absolutely not. A simple 5-second clip has causal ordering, it has action verbs, and it has precise event timing that a standard image model is going to completely miss. I mean, think about it like this. A photo of a glass shattering on the floor doesn't tell you how fast it fell, right? Or what caused it to drop in the first place. Video brings in the dimension of time. And capturing that changes the whole shebang.
But adding time creates an absolute data nightmare. 352,000. Just let that sink in for a second. That is the staggering number of visual tokens generated by just one single minute of video shot at 30 frames per second. 352,000 tokens. That massive, crushing weight of data would completely break the context windows of early LLMs. The system simply chokes. It's too much. So, AI engineers had to get highly creative and very fast to solve this.
Okay, let's dive into this. Here's our roadmap for today. We're going to hit the data problem, look at early compression attempts, explore the huge time breakthrough, check out smart sampling and pooling, talk about measuring intelligence, and finally wrap up with the 2026 playbook. Let's get right to it.
Section 1. The data problem, and exactly why video breaks those context windows.
So, because we literally cannot feed 352,000 tokens into a model for every single minute of footage, engineers have historically relied on free kind of brute force reduction strategies. First up, we can subsample frames, so maybe we only take 1 to 8 frames per second depending on what's happening. Second, we can aggressively pull the patch tokens. We smash them together using a 3x3 or 4x4 bilinear pull. Or third, we compress the data via a Q-former, which essentially bottlenecks a 16-frame clip down into just 64 learned tokens. But here's the catch. Every single one of these strategies comes with a really painful trade-off. It's kind of like trying to summarize a complex 2-hour movie by only looking at every 100th frame. You're definitely going to miss the plot twist.
Moving into Section 2, early compression attempts and the evolution of video AI.
What's absolutely wild here is the sheer speed of how fast this evolved. Back in just June 2023, Video LMS shipped as the very first open video LLM, but it was super rigidly locked to 16-frame clips using that Q-former we just talked about. Then, boom, November 2023, Video Eleva improved things by training a single unified visual encoder for both images and video, though it still struggled heavily with anything longer than 16 frames. Fast forward a bit to models like Qwen 2.5 VL in 2025, and we see this massive, game-changing leap forward that utilizes absolute time encoding.
But let's look at the harsh reality of those early methods. It's basically a game of zero-sum trade-offs. When you subsample, you lose critical temporal details. When you pool, you lose the spatial details. Actually, scratch that. You lose the really fine, high-resolution spatial details. In Q-formers, well, they kind of lose a bit of both. Because of these pretty crude compression tactics, those early models couldn't actually ground time. If you asked them when an event occurred, no way they could give you a timestamp. They just vaguely knew an event happened, somewhere early in the clip.
Section 3, the time breakthrough. This is where the narrative completely shifts to the elegant, modern solutions that finally taught AI how to understand absolute time.
Now, to really grasp this breakthrough, we need to define a crucial industry term, and that is temporal grounding. This is when a video language model can output a specific timestamp range for when an event happens. Imagine asking an AI, at what exact second does the cat jump off the table? A model with temporal grounding doesn't just say, oh, the cat jumps. It tells you it happened precisely between 4.1 and 4.3 seconds. Think about why this matters. If you're using AI to review, say, hours of security footage, knowing it happened somewhere in the clip is totally useless. You need the exact second.
And the unsung hero behind this capability? It's something called TMRoPE, which stands for Time Multimodal Rotary Position Embedding. This was the massive breakthrough in models like Qwen 2.5 VL. Instead of just giving a visual token a simple, dumb, sequential frame index like, hey, this is frame number 5, TMRoPE assigns a 3D position that includes the absolute timestamp. Because of TMRoPE, the AI's entire perception completely flips. The model literally sees a token as existing at 4.2 seconds rather than just at frame 15. Each individual visual token is allowed to rotate independently by its timestamp. This is huge, because if your frames are unevenly spaced, which happens all the time, it no longer matters. The model inherently understands exactly when that pixel existed in absolute time.
Section 4, Smart Sampling and Pooling. Let's look at how we optimize the data we're feeding into these models. So having this absolute temporal awareness completely changes our sampling strategy. Instead of uniform sampling, which is just blindly grabbing evenly spaced frames and completely missing sudden, crazy bursts of action, we can use dynamic FPS. This adaptively samples based on motion intensity. High motion segments get a ton of dense sampling, static, boring scenes get way fewer frames. The best frontier models are actually trained directly on this motion-aware adaptive sampling.
But wait, we still absolutely need spatial compression. And this is where 3x3 bilinear pooling comes to the rescue. It elegantly reduces 576 tokens down to just 64 tokens per frame. To put that into perspective, that means a heavy 5-minute video clip goes from being completely unmanageable to a highly efficient 19,200 tokens. That's nothing for modern systems. This 3x3 pooling has really emerged as the definitive sweet spot for most AI video tasks. Okay, so once the model processes this beautifully sampled data, how does it actually give us the answer? Well, free text outputs, like the AI just generating the sentence around the 4-second mark, those are easy for us humans to read, but they are terrible for software to parse. Structured JSON, or using specialized time tokens right in the output, is far, far superior. It gives us precise temporal grounding that downstream engineering systems can actually plug into and use immediately, without any guessing.
Section 5, Measuring Intelligence. With these complex systems built, how do we actually prove they're working? We look at the 4 pillars of benchmarking.
And this brilliantly illustrates how a true evaluation must stress entirely different axes. You need video MME to thoroughly test across short, medium, and long durations. You need Temp Compass to aggressively test fine-grained temporal reasoning, like did action A happen before action B? Ego Schema pushes the boundaries of long-horizon first-person reasoning, often over 3 minutes of complex footage. And finally, Video MMU just throws multidiscipline questions right at the AI. If a model can conquer all 4 of these pillars, it is truly objectively intelligent.
Section 6, the 2026 Playbook, Best Practices for Video Models. Let's tie this all together.
So the crucial point to take away from all this source material is this proven architectural recipe. If you're building today, you want a SIGLIP2 encoder fully equipped with TMRoPE for that absolute time understanding. Your sampling strategy should definitely be dynamic FPS to catch the peak action. Your pooling needs to be a 3x3 bilinear to hit that perfect token sweet spot. Your outputs must be structured JSON, and of course, you evaluate your creation against Video MME, Temp Compass, and Ego Schema. This right here is the absolute gold standard setup for 2026 and beyond.
Which leaves us with one massive, kind of mind-bending question to consider. As open models successfully adopt amazing tools like TMRoPE and perfectly ground absolute time, what gap actually remains between them and the massive proprietary tech giants? Have we essentially solved the architectural puzzle of video, leaving raw LLM scale as the only real remaining hurdle? It's a highly provocative thought, and for sure it's one that is going to define the entire next wave of AI development. Thank you so much for joining me for this explainer. Keep analyzing and keep learning.